Welcome back, and today we're going to take a look at a problem-solving technique called inductive reasoning. So, what is inductive reasoning? Well, it's the process of looking at evidence to come up with a conclusion. Let's say we're in a chemistry lab and we have three different cups in front of us. One of them, right here, is filled with acid. Maybe another one is just filled with plain water, and one more, which is filled with some kind of base. So let's say this is filled with baking soda right here. And let's say we have a piece of rock that we're interested in. Maybe that could be a purple-ish. And we're curious as to what happens to the rock when it's put in all three of these containers. If we see that the rock is dissolving in the acid, but it's not in the acid right here, but not dissolving in the baking soda, one of the things that we could say is that the acid is dissolving the rock instead of the water or the base or the base solution that we have. So inductive reasoning involves us looking at different situations, in this case, at acid, water, or baking soda, and to come up with a general conclusion based on what we're seeing. That can be very useful in math because that means we can take a very difficult problem and we can simplify it. Let's take a look at a specific example. Let's apply the power of inductive reasoning to this example problem we have right here. The problem reads, what is the sum of 1, 2, 3, all the way up to 100? So the sum of the first 100 numbers. Well, I don't think any of us are willing to sit in front of a calculator and willingly chug in 100 numbers into the calculator. Maybe if you can do it quick enough, you might be able to do it in 2 minutes. But what if you have a number? Instead of 100, maybe you have 1,000. What about 5,000? What about 1,000,000 or or 1,000,000,000? And in the case of 1,000,000,000, I don't think any of us are willing to plug and chug into a calculator. So we need to find some general way to solve to solve the problem in the case of these guys right here, in the case of these values right here. Maybe if we were given any number, we could plug into, say, a formula or some sort, which looks like which is a function, and that would spit out some sort of a number at the end, an accurate sum at the end. So instead of trying to do this with 100, let's try instead do it with just 10. We're going to take a look at the series 1, 2, 3, all the way up to 10 first, and maybe we'll find a pattern. So here I've written out our series in full. It's just 10 numbers. So now we can take a look at our series and see if we can find some sort of easy way. We could, of course, just do it with a calculator. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, and then we'll get some answer right here at the end. But because we're doing addition right here, that means we can move these numbers around. We don't have to add them in numerical order. We could add maybe all the odds first, and then all the evens. Pause the video right here to see if you can find an easier way to add all the numbers together and simplify this. So now that you tried it out, I think an easier way to do this is to add the first value with the last value. Let's try a different color right here to make things easier to see. Let's try pink. So instead of adding all the evens and odd values right here, we could maybe add the first and the last value. And then after that, the next ones will probably be the second value to the second to last value, and then we keep going from there. The reason why we want to do that is because if we add the first and last value, we get 11. If we add the second value to the second to last value, we also get 11. Now what we could do is we can just multiply to simplify our addition right here. Same thing with 3 and 8, 4 and 7, and 5 and 6. And what we would get a total of 55. So instead of doing all the addition in numerical order, we could try and rearrange the terms so that we can multiply afterwards. And that's going to be our basic idea when we tackle the series up to 100. Sometimes when we come up with an idea to solve a problem, it might not always work out, in which case we go back to our drawing board, maybe take a look at smaller values and see if we can do it again or come up with a different way of doing it. One of the most important thing about inductive reasoning is reproduction. Let's take a look right here with our series. So we have 1, 2, 3, all the way up to 100. We're going to see our trick from before is going to work with this series. So instead of writing out all the values, I'm going to make a chart. The first value is 1. Let's draw a line right here. Here we go. Our first value is 1. Our last value is 100. Our second value is 2. Our second to last value is 99. Our third value is 3, which means our third to the last is 98. Fourth value is 4. The fourth to the last value is 97, and then we keep going from there, all the way down to 50 to 51. So let's add these numbers up real quickly and see what we get. Let me switch to a different color. 100 plus 1, that's 101. 99 plus 2, that's 101. 98 plus 3, that's 101. And we can see from there on all the way down to here, down to 50 and 51, 50 plus 51, 50 plus 50 is 100, which means one more is 101. Now the question is, how many of these 101s do I have right here? Because what we like to do is take the 101s, multiply by some sort of value right here to get our final sum. Let's take a look. Luckily, with the way that we set this up, the counting has already been done for us. This is our first value. This is our second one, third, fourth, and if we keep going down, this is our 50th value. So in total, we have 50 pairs of values. In other words, all we need to do is multiply by 50. Let's write that 50 a little bit better, shall we? 50. So 101 times 50, that is 100 times 50, that's 5,000. And 50 times 1, that's 50. That means our total is 50, 5,050. And just like that, we got the sum of the first 100 numbers without using a calculator. Let's take a look at an even harder problem to see if this still works. Let's go through the same process again just to double check and also just to ingrain that idea of inductive reasoning. Let's take a look at 1,000 this time. We're going to swap over to a different color, make our table. There we go. And let's start with 1. The first value is 1. The last value is 1,000. Second value is 2. The second to last value is 999. Third value is 3. The third to the last value is 998, and so on. We keep going all the way down to 500 and 501. Yes, and you can double check to make sure. So let's undo that. Let's make these lines a little bit nicer. So let's take a look at the sum of the first and last value. So 1000 plus 1, that's 1001. 999 plus 2, that is 1001. 998 plus 3, that's 1001. And we keep going. And we're going to find that the sums are always going to be 1001 no matter what. And we'll see that at the end, we still have 1001. So in other words, the sum between the first value and last value and the pairs right here that we constructed are all going to be equal to 1001. So now the question is, what do we multiply by? Well, like always, we already have the counting done for us on the very top. The first triangle shows us the first pair. We have the second pair right here, the third pair, and if we keep going, there's a pattern. This right here is our 500th and last pair. So in terms of how many pairs we have 500 in total. And we would get, let's see, 1000 times 500, that's equal to 5 with 1, 2, 3, 4, 5 zeros behind it, 500,000. And 1 times 500, that's just 500. The sum of these two is 500,000 and 500. So that is our final answer. Let's generalize this. So now we're going to write down in general what's going on in English. We're not going to do it in math just yet. So in general, what we did was, let's draw that graph again just to remind ourselves. So there's 100 right here. Well, I'm just going to do the one for 100, 99, because the process is the same for all of them, to up to 50 and 51. Here we go. So let's write down in general what we're doing. First, we are pairing the pairs together so that the first value is, let's try a different color. So first things first, we are pairing the values so that we're pairing the first value of the series to the last value of the series, the second value to the second to last, and so on from there. So let's write that down. So the first value of the series plus the last value, we add them together, and then we multiply by how many pairs there are. So that will be, and then we multiply that by the number of pairs. So this observation right here is going to help us figure out a formula for a general subnumber n or something, because that's our goal. We want to figure out a easier way for us so that we can just plug it in and out spits a number, and we like that more than just using our hands and plug it in manually. Let's figure out a formula so that we can calculate sums easily. Let's figure out what our question is first. So our question is, what is the sum of 1, 2, 3, all the way up to some number n that we don't really know. And we don't really care at this point because, as we noticed, the process in which we solve for the sum is always going to be the same no matter what. And let's draw our chart. We're going to do the same like we did before with 100, 1,000, and 10,000, I think it was. So let's do that real quick. So we have our first value, which is, in this case, 1. And our last value, in this case, is precisely n. And we can keep going from there. The second to the last value is n minus 1. The third to the last value is n minus 2. And then we keep going until we get to n. So same thing with the top right here. Since our first value is 1, the next value we're interested in is 2, then 3, then all the way up to some value that we're going to figure out later. So let me just redraw the table out real nicely. Here we go. And then it just keeps going until we get somewhere. And that somewhere we'll figure out eventually. The next thing we would do is just to add these columns together to see what we get. So let's do that real quick. N plus 1, that's just n plus 1. If we have n minus 1 plus 2, that's n plus 1. Same thing with this column, with the third column, n minus 2 plus 3 gives us n plus 1. And we can say in general, whenever we add the first value and the last value together, we would definitely get, in this case, n plus 1. So let's take a look at the pairs of values. How will we figure out the pairs of values in this case? Well, same thing as before. The pairs of values has already been counted for us. Before, when we had 100 values, we had 50 pairs of values. If you have 1,000 values, we would have 500 pairs of values. And if we have 10,000, we have 5,000. So in general, we could say that we're simply just taking the total amount of values and just dividing them by 2. And that's how we're going to get our pairs of values. So we take our total amount of value, which is n, and we're just going to divide it by 2. So let's write this out on another part of this canvas here. So we have n plus 1 from our sum of these pairs of values, and what we're doing is we're multiplying it by a factor, in this case n over 2, because that's how many pairs of values we have. So now let's try this function out. We're going to take it out for a spin, and we're going to plug it into all 3 of these values right here and see if they work. That's our last step in inductive reasoning. So now we're at the end of our inductive reasoning. We have found an equation or a formula to solve for the sum of the first n values. This is the sum of the first n values. Let's take a look at the problems that we did before. The first one we did was up to 100. The second one we did was up to 1,000. And the third and final one was up to 10,000. So let's see if this formula works. So first things first, since n is equal to 100, let's write this out using the same red color that I did before. Plus 1 divided by n over 2. So that should be 100 on top right here. And what do we get right here? So let's take a look. 100 plus 1, that's 101. 100 divided by 2, which is 50. And at the end, we get 50, 50. Let's double check here. 100 times 50, that's 5,000. 1 times 50, that's equal to 50. So our 50-50 works. In the case of 1,000, we have 1,000 plus 1 times 1,000 divided by 2, which means it's 1,001 times 500, which is, let's see, 500 times 1,000, that's 5 zeros behind it. 1, 3, 4, 5. And since we have 1 times 500, that 0 should be a 5 instead. Let's fix that. 500. Here we go, a number that we've seen before. So let's just double check one last time with 10,000, just in case if it falls apart. But because we like double checking. So 10,000 plus 1 times 10,000 over 2, which is 10,001 1 times 5,000, which gives us, let's see, 1, 2, 3, 4, 5, 6, 7, 7 zeros behind it. 5 times 1, 2, 3, 4, 5, 6, 7. There we go. And 1 times 5,000, that means the fourth zero is a 5. Let's double check right here one more time. 10,000 times 5,000. That's 5, 1 with 4 zeros plus 3 more. 50,000. And 1 times 5,000 is just 5,000. And there we go. So, inductive reasoning. Very useful when you have a big problem that you need to solve. In fact, this formula right here, n plus 1 times n over 2, has been in use for years. It's used in every single mathematical field you can think of: algebra, geometry, topology. It's used in graph theory, where we can measure the number of vertices, which is used in studying how Facebook works and how Twitter spreads its information. This function that we created is and has been a staple in many mathematical fields. So, I hope that you enjoyed. Try it out for yourself. Inductive reasoning is very helpful when it comes to solving problems.